Alrighty, welcome back to operating systems. So today, fairly chill lecture. This is not testable, this is not on the midterm, this is not on the final, this is not on anything. This is a prelude to networks and, well, guess what? If you used a web browser or if you communicated across different computers, you've used sockets. And turns out, aside from the setup, you already know how to use them because they're represented as file descriptors. So you can just read and write. So let's get into it because it's, you use them. If you use the internet, most of you use the internet, so you use sockets. So sockets are just another form of IPC or inter-process communication. We've seen pipes, we've seen signals, we've also briefly talked about shared memory. So the thing with all these mechanisms of IPC is, well, they all have to be on the same physical machine. So all the processes running on the same machine, in order to share memory, well, both processes have to be able to access the same memory. So what about if the processes are not on the same machine? So sockets are the IPC mechanism to communicate between physical machines where the processes are running, like I said, on different physical machines. Typically, this will be done over a network. So you go to google.com. You are communicating with Google's process that sends you the source code for google.com, then your web browser renders it, and a whole lot of things go on with that, but this is networking in a nutshell. So for networking, there's typically a server and a client, and a server is basically the thing that you connect to. It waits for a connection, you connect to it, and then once you connect to it, you can send data back and forth between it. So if a server is using a socket, it has to follow 4 steps, and this is the most complicated, the most number of steps you have to do to use a socket. So they're all system calls. They have all the usual C wrappers, so if they fail, they return -1 and they set error no. Like every single function we've pretty much seen, that's a system call. So the first step is a socket system call, and that, unsurprisingly, creates a socket, and it returns you a file descriptor. So we'll see what the arguments to that are later, but all we have to know right now, you create a socket, and then step 2 is you bind the socket to some location. So a socket by itself doesn't do anything. It needs to have an address associated with it. So you can bind it to some location. If you're on the same physical machine, if you want to use this, you can bind it to like a file name. Otherwise, you can bind it to an IP and a port, and then it will use the internet or your local networking or whatever you have. The third step is to say you are listening, and this indicates to the kernel that you are accepting connections. This also lets you set a kernel-determined queue for how many connections it will hold, waiting for your program to actually accept them. Then fourth step is to actually accept the connection. So this returns the next incoming connection for you to handle. Accept is a blocking system call, and whenever it's done, if it doesn't have an error, it will return you a file descriptor, and then you can read and write to it, and then magically that information will go across the network. But otherwise, it's the exact same thing as we've been doing. So if you're a client, you have 2 steps, much easier time. One connection is just one socket, so you do a socket system call, create a socket, and then you do a connect system call that says what location do you want to connect to. So a server needs to be listening on that same location in order for the connection to be successful. Otherwise, you will get an error. You'll return -1. It'll set error no. It'll tell you why. If connect is successful, your file descriptor from socket is now valid, and you can now read and write on that file descriptor, and the opposite thing will happen on the server. So you can send information to the server and read information from the server. So let's go over the system calls really briefly. So the socket system call sets the protocol and the type of socket. So it takes 3 arguments. The last one is no longer used, so it's just always 0. So domain is the first one. It's the general protocol basically saying what the location is you want to connect to. The three ones you will see 99.9% of the time are AF Unix. So that's for local communication on the same machine, and you're connecting to a file name. So this is what a lot of programs use. So like if you've used Docker or anything like that, guess what? It uses that. It uses a Unix socket. If you set it to iNet, it wants an IP address, and it means I'm going to connect to something across the network. If I do iNet 6, that's for IPv6 because, well, once you get into the networking class, you realize that IPv4 addresses are only 32 bits. Those are only like 4 billion devices on the internet, and since everyone plugs their toaster into the internet, we ran out of IP addresses some time ago. So this is an IPv6 is basically just a bigger number, and the type is usually one of two options, a stream or a datagram socket, which you've probably never heard of before, but you may have heard of the term TCP. So if you've heard the term TCP, that's what a stream socket is. So that means all data you send across that socket appears in the same order in the client. So if I send, one string and then another string, then the server is going to see those in the same order. And you also have a persistent connection between the client and the server. They acknowledge each other all the time to make sure that they're still alive and you still have an active connection. Otherwise, if that connection drops because the Wi-Fi drops out, which what happens in this room a lot of the time, then you'll get notified of it. It'll say connection lost, and you'll be notified of it. You'll get an error immediately. So this is a reliable form of communication, but it may be slow because it goes against how real networking works. So with real networking, it's something closer to datagram sockets, and that uses UDP. Basically, all that does is send messages between the client and server, and it just sends packets. If you get into the networking course, you will realize that packets have fun journeys. So there's no guarantee if you send two packets to the same server that they will take the same route. One might go through Japan or something like that, while the other takes a direct connection. You're not guaranteed which one takes which path. They won't be guaranteed to be received in the same order. Like someone could you could be using Wi-Fi, someone could turn on the microwave and screw up your Wi-Fi signal. Lots of things happen. For UDP ones, there's no persistent connection between client and server. You just send a packet to them and you pray, and that's about it. So there's no persistent connection. Your messages might be reordered because you're at the mercy of the actual network, which again is a whole nother course. They might get dropped, the machine might not exist, and you're not going to know about it. So if you send a packet off, you're not even sure if it ever arrives there. So this is fast, this is close to what networking actually does. It doesn't do any fancy stuff. It doesn't care, and for some applications this might be more warranted. So for instance, if you did video streaming or something like that, well, that's kind of like a real-time system, right? You have to send a certain number of frames a second, otherwise you don't see it. If the connection drops or something like that, well, I might not want to resend it if you're listening to a live broadcast because that time's already done. I should just skip it, go ahead to the next one, something like that. Or like if it was a game or something like that, resending a packet, not going to work because the whole state of the world has changed since then. So resending it doesn't even make sense. It's not going to be accounted for or anything like that. So typically use UDP if those things are true. If you want things in order, some people get clever and think that UDP is just really fast because it doesn't have any overhead. But then they want to get things in the same order, and then they implement TCP themselves on top of this, and they do it badly, and they have bugs, and they should have just used TCP to begin with. So know what you're going to use, and again, if you need that concept reinforced, take the networking course. All right, all right, that aside, back to the system calls. So the bind system call binds a socket to an address or a location, takes the socket as the first argument, and then, well, because it's C, it takes an address to a struct called sock address, or sock adder, sorry, which is just short for socket address. And then because it's C, it needs the length of that structure because otherwise there's no way to figure it out. And there are different structures depending on what you're trying to connect to. So if you are connecting to a Unix socket, you use this sock adder underscore un. Don't ask me why they didn't want to add 2 extra characters so it said Unix. I don't know, but this is just a path, so it just looks like a file. Then there is socketdir underscore in instead of inet. Again, I don't know why they saved 2 characters, but this is going to be an IP address like 8.8.8, something like that. And then inet6 or IPv6 or in6 is going to be an address that is much longer, so it'll be hex digits separated by colons, and it's kind of ugly. So the third step in our server journey is a listen system call. Sets the queue limits for incoming connections, basically how many connections the kernel will hold for us before it starts dropping them. The first argument is still a file descriptor returned from that socket system call, and this int argument is just how long of a queue do you want the kernel to maintain. So if you set this to 0, the kernel picks for you. So the kernel has a default. Generally, the kernel developers are smarter than me, so then just pick 0, let the kernel figure it out. If you have problems, you can come back and change it later, but generally, kernel is smart. All right, the last step is the accept system call, and it is a blocking system call that will block until there's a connection. So it takes that socket, and then optionally, it will also take a different address. If this was a datagram socket, you could just accept connections from any address you really wanted to, or without setting it up. In this, just set them both to null and ignore it. We're just accepting connections on the socket. So this will block until a new connection is formed, and then when it returns, the return value is an int. That's a file descriptor representing that connection. So you can do read and write system calls to it like it was anything else. All right, so we're almost done. So this is in the client. It just has a connect system call that allows a client to connect to an address. So it takes the socket file descriptor, return from socket, and then takes the same socket adder and also needs a length that we saw in the bind system call in the server. So they have to match if you want to form a connection between a client and the server. So the only difference is if this call succeeds, it doesn't return a new file descriptor. It just makes that file descriptor you got from socket actually usable now. So now you can do read and write system calls on that. So that's a lot of talking. I like code better, so let's switch to the code example. So let's get rid of this. We can make that, well, sure, we can make that bigger. So here is the server code. So the server, remember, has to do those 4 steps. So before I even start, I'm going to register 2 signals. We know kind of what that does. I'm registering a signal for sigint, which is what happens when you hit Control-C, and then sigterm, which remember, that's like asking a process to exit nicely if you just kill it without -9. So that is the nice way, and we will figure out why I'm doing this very shortly. But let's get back into our 4 steps for the server. So we have a socket system call. We're going to use a Unix location and a stream socket. So those, if you look at the documentation, they're just little macros. They're numbers. That's what they're called. So of course, we check for errors because if you learn anything from Lab 2 or learn anything from this course, hopefully it's checked for errors. And if you see an error, either handle it properly, or if you don't know, if you have anything that's unexpected, just exit immediately. So here, I check if there's an error, and then I exit immediately if there is. Next step, I need to bind it to a location. So I create a socket address for un, or the Unix socket. Having a structure and setting it like this, having curly brackets and a 0 might look weird. That just 0 initializes the whole structure. So it fills that full of zeros, and 0 initializes it explicitly. Then here, I set the sun family field, which is basically what type of socket address there is, which might seem redundant, but this is basically C's way of implementing C++ classes. So you always have to say at the beginning what this structure actually is. So it might seem redundant, but here we specify that, hey, the socket address is a Unix socket. Then the only path we have to set is the sun path, and it is a string. So we will copy from a static string into it. So this expands to just example.sock. So I'm setting sun path to example.sock, and I will copy the bytes from that string with the size of that whole structure -1, because I want to make sure that there's always a null byte there if I fill up the structure. Then of course, I check for errors. If there is an error, I exit immediately. Then I just do a listen system call. Default argument is 0. If there's an error, I exit immediately. Then the fun part. So this, while true, this is basically your web server. This is what your web server will do. It just has an infinite loop that just accepts connections. So if you've ever connected to a web server or anything, way deep in the code, essentially it looks like this. So in an infinite loop, I call accept with that socket, and whenever this returns, I have a new connection. So now I have a new file descriptor that represents the connection. I'll call it connection FD because that seems appropriate. Check if there's an error. If there is, I immediately blow up. Otherwise, I just create a static string that says hello there. Then I determine the length of the string and then add 1 because I want to send the null byte just to make my life a bit easier in the client. Then here I do my write system call. So I just write that string, all of it, to that file descriptor represented by the connection file descriptor. Here I will check for errors, and then I will check that the number of bytes written is equal to the length I requested. Otherwise, I would have to retry it or something like that, and I don't want to rewrite the code. I'll just exit if that case happens and deal with it later. Then finally, I close that connection and check for errors. Then after I close the connection, just goes back up to the top of the loop and accepts the next connection. So new client can connect, send a message, new client can connect, send a message, new client can connect, so on and so forth. So the reason why I have a signal handler is because, well, this is an infinite loop. I can't just exit the program without giving it a signal or requesting it to shut down. So that's why I register signal handlers, because I create that example.sock file and I want to clean it up. So I register a signal handler. I say I want handle signal to run. Inside of that, I just write an assert to make sure that it's the signals I expect. In case I try and change my program later and I forget that, I handle other signals. Because all I'm going to do in the signal is close the socket, clean up all my work, and be done with it. So in close socket, I close the file descriptor representing the socket, which is why I made it a global variable, so I can actually access it in my signal handler. And then I have this unlinked system call, which we have not seen before. All that does is get rid of this name. So it just gets rid of example.sock in the current directory. You haven't seen this yet, but you will. So there is, fun fact, whenever you remove a file, it doesn't delete anything. There's no remove system call or anything like that. The closest thing is just an unlink, which just gets rid of that name in the directory. And then you hope the kernel actually deletes something for you if it can delete it. But if you strace rm, you'll see that it calls unlink. There's no rm system call. We will see why that is once we get to file systems. All right, so that is the server. If I try and run it, whoops, I see address already in use because I screwed up. All right, if I try and run it, it just sits there, it runs, it doesn't do anything, because if we strace this, it would be blocked on that accept system call because it hasn't returned yet. So let's see what the client does. So in the client, same thing, creates a socket, it's a Unix socket, it's a stream socket, check for errors. This is also the exact same thing. I'm connecting to a socket address representing a Unix one. It's just going to be a path, so it's going to match between the client and the server. So the client also wants to connect to example.sock. So in here, because we're in the client, I just call connect using that file descriptor returned from socket and the address of the socket address and the size of it because it's C. And then if that is successful, that file descriptor now represents that connection to the server. So here I can just create a buffer of size 4096. Now we know why I picked that number. It's because it is the size of a page, and the kernel loves pages. So creates a buffer of a page, then creates this bytes read variable. It puts a read system call and a while loop just in case it needs to go over and over again. In this case, well, it'll only return once. So we just keep reading while there's bytes to be read, check for errors, and then all we do is print the string that gets received, and then close the file descriptor, and that's it. So I can open a new terminal, and now if I run the client, well, I have to go to the right directory first. I receive hello or hello there. Yay. So I received that from the other program that is running. So that information is clearly coming from the server process. So I'm communicating between processes. I don't have to use pipes. They don't even have to be related at all. Like the two processes can be completely unrelated. As long as you know the name of where to connect to, your process can just connect to it, no problem. So any questions about that or anything you want me to do to break this? Because this is the internet. Yep.
What happens if you don't unlink the socket?
Yeah, so the question is what happens if I don't unlink the socket function? So we can see what that does. So in the server, let's see, the old comment out. So right now, if I kill the server, it's going to unlink it. So here, let's see. So here there's example.sock there. So it looks like a file, but you can see it's like in this pink color. So it's a file of socket type. So if I kill the server right now, it won't have my change of commenting out unlink. So if I control C it, the server is now done. And if I look at the directory, example.sock is gone because unlink happened. So now if I try and run the client, well, guess what? It says no such file or directory because that name no longer exists. So what happens if I forget the unlink? Then I can rebuild my server, run it again, and then in the client, hey, it now can receive data because it is now listing. But now, if I kill the server, well, the example.sock is still there. And if I try to connect to it in the client, it just says connection refused. So good thing I checked for errors. And you've probably seen this message if you used your web browser, right? You've seen connection refused. I didn't make up that thing. It just came from this failing. All right, any other questions with that? And also with that, also if I try to run the server, because example.sock still is there, if I try and bind it, it says address already in use because that file already exists. So that's why you should clean it up. If you wanted to write a quick and dirty server, well, the server could just see that, hey, is that file name already there? If it is, just unlink it then, but you should probably just clean it up. So that's why I just have to remove it, which basically does the unlink for me, and then I can run the server again. Lots of stuff, lots of fun stuff. All right, any other questions? That's the internet, that's a web browser. That's like a very poor web browser, but it's the same thing. So if you want, create a socket, you can connect to anything you want, connect to google.com, just figure out whatever IP address they're using today, and just send it some random bytes and see what happens. Nothing's disallowing that. It'll probably be like, what the hell are you doing, and close the connection immediately. In fact, even what I wrote here is pretty bad because this client, it expects a string, and it expects a string with a null byte, so I could just completely screw up my client right now. This is why you should not trust things. So I could probably exploit myself. Let's see. So let us screw up. So we can do this. So that means I will not write the null byte to the client. So let's have some fun with that. Let's make a fun server. Oh, address already in use because I commented out, I guess. All right, so in this case, if I connect to the client, now it gets hello there, and it didn't crash. Wait, did I compile? I think I was still uncompiled. Huh. Weird. It must have assumed that. Oh, it probably zero initialized that memory, so I got myself lucky where I didn't overflow my buffer, but you're not guaranteed of that. But you shouldn't trust information from the server. That's how exploits happen, like just sending random data that servers don't expect. That's how a lot of exploits happen because they might give you a response that kind of makes sense or share some memory with you that they shouldn't or something, and that's how exploits happen. Yeah. Yep.
Sorry, I'm just curious. Does DDoS relate to any of those?
Yeah, so the question is, does DDoS relate to any of those? So kind of. So DDoS relates to essentially this queue size here, right? So the kernel has a bit of DDoS protection built into it, at least for connections themselves, where it will only hold a certain number, and if you try and connect past that, it'll just start dropping them. So that's kind of like a DDoS protection. Sometimes DDoS just means you are wasting the server's resources, and the kernel can't help you with that. So if this server like held the connection open, as long as your client held it open, you could just open thousands and thousands of connections, and then suddenly it's going to run out of space eventually, run out of file descriptors, run out of something, and then that will be a denial of service attack. So that's one instance of it, and that's denial of service on a single machine. You could have multiple machines hosting your network or something like that, and then another denial of service, try and do that to all of them, or just overload them, or give them useless work to do, or something like that. Tons of denial of service you could do. But your defense to that is like, hey, if I see someone that's opening a connection and they're not doing anything I expect with it, just drop it. So you can, that's one thing to protect yourself, kind of related, but the kernel can only do so much to help you. So it can set the queue length and then start dropping connections, but it can't handle what you do with them. So that's, was that in the networking course or something?
No, I just jumped out of my mind.
Okay. Yeah, I had the same question last lecture, so I thought it was some course or something.
Maybe you do want 15 terabytes of network data in one day.
Maybe. But yeah, so here too, this is also kind of bad too because I only handle one connection at a time. Someone brought up the point like, hey, after I accept, can I just fork? Sure, you could fork. You could have another process handle that connection. Then those two processes could happen at the same time. The other one could just try and connect to another one, make a new process for that connection, so on and so forth. Then you can handle a bunch of connections at the same time. Turns out processes are a bit of a big hammer, and these connections are usually really short-lived. So that motivates threads, which is next lecture. But yeah, basically if you just do that idea, but use threads, that's a good web server. This is a crappy web server that can handle one connection at a time. But if you wanted to handle multiple at a time, right now you could just fork after every one. Yeah. Oh, that was a stretch. All right. Yeah. Can I what? I have to look up the format for all that and what their IP address is today and stuff. And if I send it garbage, it's going to probably as soon as it doesn't know what the hell I'm doing, it's just going to close the connection immediately, which is what the sane thing to do is. So if you wanted to write a web server, well, you connect to google.com and you have to figure out like the HTTP protocol and figure out exactly what to send it in order to get a response out of it. Otherwise, most web servers, if you send it something unexpected, it'll just be like, nah, I'm good, and close it and just carry on. All right, any other questions? We have learned the internet today. Didn't expect that in operating systems, did you? So, why is this here? Well, I mean, it's related, motivate sockets, and you actually already know it already aside from the setup. So the setup is just something you like look up once and then you copy and paste it for the rest of your life. And the rest of it, just using a file descriptor, is what you already know how to do. So there is some exceptions once you get into the networking course. So instead of read and write, there's also send and receive system calls specifically for sockets that do essentially the same thing, except they take some additional flags to control what happens with them. So some examples are message out of bound, which you have to ask the networking people what that means. I don't really know. Then there's like peek. So that means I'm going to look at a few bytes of the data without actually consuming it in the kernel. So I could do a read call later and get all the information. And then there is this funny one that's called don't route, which doesn't look like it makes sense. So if I'm connecting to the internet, why would I want to send information without routing it? Because even if I need to hop to your computer or something like that, well, there needs to be some routing involved. So, turns out that, well, guess what? Routers are also use Linux. So they would want to use this don't route because if you are implementing a router yourself, you want to make sure that packets don't take an unexpected leaps or anything like that. You want to just make sure that whatever you send goes directly to the device you intend because you are the router. And if it was also routing while you were trying to do that, you might get into the situation where you route back through yourself and then you create an infinite loop with the packets and then they never actually arrive and it's real bad. So that's why there's something like don't route, which you will never use unless you are implementing a router. Maybe you look at that in the networking course, I don't know. And then there's like send to, receive from, which basically you can just tack on an address to them, and they're pretty much just used for datagram sockets. All right, cool. Now you can do the web. You are internet, so you can perform networking through sockets. You can strace your web browser. It uses sockets. Any program that connects to the internet uses sockets. Again, everything has to use a system call, so you can strace everything. Don't believe me? Go ahead, strace Chrome. It's going to create lots of sockets. So sockets are just IPC. They're not anything actually that new aside from the setup. They're just IPC that can go across physical machines. Basics are they need an address. Either it's like a file path for a local one or an IP address. Two types, stream, datagram, which are basically TCP and UDP. Servers have 4 steps. They need to create the socket, bind to an address, listen to it, and say how deep the queue is, then accept connections. Clients, all they need to do is create a socket and then connect to an address. Yay, so now we can use the rest of the time for whatever you want. So just remember, I'm pulling for you, we're all in this together.